Math 1314, section IC1, spring 2022, Tyler Junior College, section 7.2, polynomial functions, video 6, zeros and x-intercepts, unfactored polynomials. Okay, so in the past two videos, we've learned about zeros and x-intercepts, where namely we put the function equal to 0 and solve. And in fact, I want to draw that here, just a reminder that this means that we want to find solutions to f of x equals 0. And by the way, that's the definition of the zero of a function, or zeros of a function, regardless of the type of function, whether it's polynomial or something else. But finding those leads to x-intercepts, and we've done it so far for factored polynomials, which was convenient because when you solve something like this, where the left side is factored, then the zero product principle says set each factor equal to 0 and solve. And in the most recent video, we also talked about the effect of multiplicity on the x-intercepts. Multiplicity being the power on the factor that produced the x-intercept. And if the multiplicity was even, then the graph would touch the x-axis and turn around. But if it were odd, in other words, do something like this. But if the multiplicity were odd, then it would actually go through the x-axis to the other side. Now, if your polynomial is not factored, it doesn't change anything, really. We still have to solve this. We still have to look at multiplicities and determine if the graph crosses the x-axis or touches the x-axis and turns around. But the hang-up is when we're solving this equation here, it's easier if it's already factored. Excuse me. So if it's not factored, guess what we have to do? The answer is factor. All right, so let's clean this up and let's take a look at an example. A little bit more, there we go. All right, find the zeros, multiplicities, x-intercepts, and x-intercept behaviors, whether you cross the x-axis or touch the x-axis. And notice that our function is not factored already. F of x equals negative x to the fourth power minus x to the third power plus 12x to the second power. Now, our approach isn't going to change. We're still going to set up and solve the function equal to 0. So we need to solve negative x to the fourth power minus x to the third power plus 12x to the second power is equal to 0. But the problem is this isn't factored. And remember, when you're factored, in other words, if I look like this, 2, maybe 3 factors equal to 0, then we would just put each individual factor equal to 0, whatever the contents of the parentheses are. Because the zero product principle says if a multiplication problem is equal to 0, then at least one of its factors must be 0. The problem is we don't have factors. To be factored means to be written as a multiplication problem. To factor something means to rewrite it as a multiplication problem. So we're going to have to factor this. The problem with that is that there are multiple techniques for factoring. I'm going to remind you what some of those techniques were. Earlier in the semester, there were some videos that I recommended to watch when one of the Math 0314 weekly work assignments was about factoring. So if you go into Canvas, go into modules, Canvas in the Math 0314 section, go into modules and open up the Math 0314 weekly work module. It was in weekly work 4 where I recommended watching these videos about how to factor polynomials, factoring by GCF, greatest common factor, factoring by grouping, factoring trinomials whose leading coefficient was 1, factoring trinomials whose leading coefficient was not 1, and factoring a difference of squares. Now, if you're comfortable with your factoring techniques, then this video's content, the one that I'm making right now, is going to be pretty easy. But if you struggle with factoring, then I strongly recommend going back to Math 0314 weekly work module. Right before weekly work 4 were the reviewing the factoring review videos. Watch as many as you need to. Watch them more than once if necessary. But factoring, as I warned you in the past, is a skill that's not going away. And we're about to use it here. So as I cite these factoring techniques, I'm not going to reteach how to factor them. I'm simply calling out the move that we're doing. First, we're going to factor out a greatest common factor. To do that, we need to ask ourselves two questions. What's the most number of x's everybody has in common? And what's the greatest number that divides all the coefficients? Well, there are four x's, there's an x to the fourth, an x to the third, and an x squared. And the greatest number of x's they have in common is x squared. It's a little bit ironic, but the greatest common factor is the least power on the exponent. Now, as far as the coefficients, it doesn't look like there are many coefficients, but there's three of them. -1 is implied there, -1, and +12. Now, the greatest number that will divide into all of those is 1, but as part of the GCF move, if you're taking out a greatest common factor and the leading term is negative, then your GCF should also be negative. So we're going to factor a negative x squared out of this trinomial. We'll close it off when we need to. All right, by factoring out a negative, everybody's sign is going to change. By factoring out an x squared, everybody's power is going down by 2. So the negative x to the fourth changes sign to become positive, lowers its power by 2 to leave an x squared. The next term, negative x to the third, changes its sign to become positive, lowers its exponent by 2 to become x to the first power, or just x. The positive 12x squared changes its sign to become negative and lowers its power by 2, but it only has an x squared to begin with, so it loses all of its x's. We have negative x squared times x squared plus x minus 12. And now the part inside the parentheses is just a trinomial whose leading coefficient is 1. In other words, you would watch this third video, first one for GCF, you'd watch this third video for factoring trinomials whose leading coefficient is 1. If we did that, we would get two parentheses, and we would need two numbers whose sum is +1, whose sum is 1, and whose product is -12. The two numbers that multiply and add that way are +4 and -3. And at this point, the polynomial is completely factored. And now that it's completely factored, we simply have to set each factor equal to 0 and solve. Negative x squared is equal to 0. X plus 4 is equal to 0. X minus 3 is equal to 0. If we take them from left to right to left, x minus 3 is easy to solve. We just add 3 to both sides and get x equals 3. X plus 4 equals 0 is easy to solve. We just subtract 4 from both sides, get x equals -4. Now, the negative x squared equals 0 looks tricky to solve, but let me give you a hint about solving a factor equal to 0. If that factor is a single term, no pluses, no adding, no subtracting, just a single term equal to 0, it's going to give x equals to 0. Because to get the negative x squared by itself, you would have to divide by -1, which won't change the 0, and square root, which still won't change the 0. The only way 0 becomes something different is when you add or subtract something to it. But since I'm not doing any adding and subtracting moves, the 0 will not change, and we'll get x is equal to 0. Now, we do also need to make note of the multiplicities, which I'm abbreviating MULT. The multiplicity is just the power that was on the factor. That was supposed to be red. The power that's on this factor is 2. So my multiplicity is 2. This factor did not have a power on it. We'll use blue for this one. This factor did not have a power on it, but it was an implied power of 1. And so the multiplicity of x equals -4 is 1. And the last factor, which that was supposed to be in black, the last factor also, we'll do green on this one, also had an implied power of 1. And so the multiplicity for the last factor is 1. So what does this mean about x-intercepts and crossing and touching and turning? Well, if your multiplicity is odd, you cross the x-axis. So we can say, and I'm going to type this because it'll be cleaner, we can say that the graph crosses the x-axis at -4, so as an ordered pair, -4, comma 0, and 3, but as an ordered pair, 3, comma 0. See if we can get rid of that line break there. Get rid of that line break. Come on, there we go. Graph crosses the x-axis at -4, comma 0 and 3, comma 0 because of the odd multiplicities. And the graph touches the x-axis at, let's see, that would be at 0, comma 0 because of the even, can't type today, multiplicity. Let's take that down a font size just because I think it'll look a little bit cleaner. There we go. That's too much. 24 is what I was going for. All right, so there's the summary of the results. Let's try one more, and that's all there'll be in this video. Find the zeros and multiplicities and x-intercepts and x-intercept behaviors, cross x-axis or touch the x-axis, of this function, g of x equals x to the third power minus 3x squared minus 9x plus 27. Again, we're going to solve this equal to 0, and it's not currently equal to 0. Excuse me, it's not currently factored. Well, it's not currently equal to 0 either. We're about to fix that. We need to solve x to the third power minus 3x to the second power minus 9x plus 27 is equal to 0. This is not factored, so we need to resort to a factoring technique. If you rewatch the factoring videos, you'll know that a good suggestion when you're factoring a polynomial with 4 terms is to try grouping. Now, that doesn't always work with the 4-term polynomial. It will for this one. Very soon, we're going to see what to do when it doesn't. But grouping basically works under the premise that you're doing 3 GCF moves in a row, 3 greatest common factors. By looking at this not as one 4-term expression, but as a pair of 2-term expressions by splitting this into 2 pairs of terms. The split always comes before the sign in the middle. And then you GCF each half. In the first half, x to the third power minus x to the second power, I can factor out an x to the second power, and that will leave x minus 3. The second half, I can factor out a 9, but as a GCF move on the second half, because the leading term is negative, and when I say the leading term is negative, I mean this term right here. Because that leading term is negative, the negative 9x, that means when I factor out a GCF, it needs to be negative. So I'm going to factor out a negative and a 9. So from each of the last 2 terms, I will divide it by 9 and change its sign. Negative 9x divided by negative 9 is x. Positive 27 divided by negative 9 is negative 3. And as a grouping problem, it's doing what's supposed to, because as a grouping problem, these 2 parentheses are supposed to match, and they become one factor. Go ahead and highlight that in yellow. And then the remaining pieces, the greatest common factors that I took out the first time, the x squared and the minus 9, they become the other factor. Okay, so hooray, we're factored, but we're not factored completely. Why? Because you may notice, or you may not notice, that the second factor, which I'm going to try to draw an arrow around to, this is a difference of squares. Let me type that. This is a difference of squares. It's funny how you have to remember, well, everything. Difference of squares. Now let's draw that blue arrow to it again. Difference of squares being the last factoring technique that was covered here. Factoring review 5, difference of squares. As a difference of squares, you can factor it. Well, first let's bring down the first parentheses, x minus 3. Trying to get it back in black here. There we go. The first factor is x minus 3, but the second factor, which we'll just do in blue for emphasis. To factor x squared minus 9, you just split the x squared into x times x, split the 9 into 3 times 3. One gets a minus, one gets a plus. And now it's completely factored because, well, what else are you going to factor? Now you may notice at this point, 2 of the parentheses match. There's a pair of x minus 3s. So we're going to go ahead and write them once with the power of 2 to mean that the factor was in there twice. Why? Because the multiplicity discussion is based on powers on the factors. So if we see matching factors, we need to merge them together to see what power they have. At this point, it's a straight shot to the end. We solve x minus 3 is equal to 0. That gives us x equal to 3. And we solve x plus 3 is equal to 0. That gives us x equals negative 3. The multiplicity of x equals 3 is 2 because that's the power on the factor. And the multiplicity of x equals negative 3 is 1 because that is the implied power on the factor. And what does it mean when the multiplicity is even? That means you cross the x-axis. No, it doesn't. When the multiplicity is even, you touch. So the graph touches the x-axis at x equals 3 and y comma 0. Remember, it's an x-intercept, so the y-coordinate is 0. And the graph crosses the x-axis at the x-intercept with the odd multiplicity. That would be x equals negative 3 comma 0. So really, when you're finding the intercepts and multiplicities and the intercept behavior, cross versus touch of an unfactored polynomial, it's just the same as if it were factored. The only difference is, in order to find the zeros, we have to get it factored first.